Okay, we're gonna start to talk about optimization problems today. We've got a few different methods to work with, and I'm gonna split this into two videos. So the first method that we're gonna look at right now is a method that involves mostly algebraic techniques working with the function. So if we're going to deal with optimization problems, we need a good definition of what a maximum or minimum value is, where it occurs, and all of that. So there's my pen. So we basically have two parts to this definition. All right, the first part, I'll read it to you and then I'll put it on the board so you can write it down. All right, if f has a local maximum or minimum at a point, a, b, and the first partials exist at AB, then the first partials are going to equal 0 at AB. All right, so if f has a local, sometimes called relative, max or min at AB, then, and the first partials exist. Forgot about that part. They have to exist before we can do anything with them. And fx and fy exist at AB, then f of AB is going to, fx, the first partials, fx of AB is going to equal 0, and fy at AB is going to equal 0. All right, so basically, if we know that we have a local max or minimum, then we know that the first partials exist, and we know that they're going to equal 0 at that point. All right. In addition to that, if we know that the first partials are 0, then we can call AB a critical point. All right. So if fx of AB equals fy of AB equals 0, all right, so if the first partials at AB equals 0, then we call AB a critical point. All right, keep in mind, having a critical point does not guarantee you a relative maximum or minimum. The same is true in R2. I mean, if I drag you back to Calc 1 again, as I frequently do, and you take a look at the function y equals x to the third, all right, y equals x to the third has a critical point at x equals 0, but that is neither a maximum point nor a minimum point because the function doesn't change. It is increasing everywhere. So again, just because you have a critical point doesn't guarantee you a maximum or a minimum. All right. Okay, so what are some of the methods we could use to go about finding these? Well, let's start with a function. So I have a function here, f of xy is x squared plus y squared minus 2x minus 6y plus 14. All right. All right, now again, if you think back to what we did in chapter 12 or the end of chapter 11, I don't remember where it was. It might have been the end of chapter 11 where we talked about the quadratic surfaces. This is going to be a paraboloid. All right, I'll show it to you in a little bit. I've got all my functions today up on GeoGebra. But let's go through just using the definition. So I would like to find any relative extreme points on this paraboloid. All right, so the first thing I know is if there is a local max or min, then the first partials exist and they have to equal to 0. So let's find the first partials. So fx, xy. All right, so with respect to x, this is going to be 2x. That's going to be 0. That's going to be minus 2. That's going to be 0, and that's going to be 0. Fy, all right, again, with respect to y, that's going to be 0. 2y. That's going to be 0, minus 6, and that's going to be 0. So there are my first partials. Now again, if x has a local max or min, then those partials are going to be equal to 0. So let's see where they're equal to 0. So 2x minus 2 equals 0 means that x is 1. And 2y minus 6 equals 0 means that y is 3. All right, so when I take a look at what happens at each of those points, all right, so what this means is I have an x and a y, right? So that means that I have a critical point, right? So 1, 3 is a critical point. All right, so now the question is it a max? Is it a min? Is it neither one? All right, so what I can do with my original function here is let's take a look at what happens along some paths. So the easiest thing to do here with this one, all right, let me change my phrasing there. The most straightforward thing to do with this one is going to be to take the original function and complete the square on it. So I'm dragging you a little bit further back than Calc 1 this time. All right, so if I complete the square on this, I'm going to assume that you guys know how to do that. All right, I'm just going to do that for right now. If you need help, we can talk about it when we meet. Fxy, when I complete the square, is... All right, sorry, I forgot to mute my phone. Fxy, when I complete the square, is going to be x minus 1 squared plus y minus 3 squared plus 14. No, plus 4, I'm sorry. Plus 4. All right, so just remember half the middle term squared, add it and subtract it. Again, if you need that in detail, we can talk about it on Thursday. For crying out loud. Okay, shut up, phone. All right, so I have my completed square form. Now, with the completed square form, that gives me more information. All right, so if I take a look at this, each of these terms is going to always be positive, right? So x minus 1 squared is always greater than or equal to 0. All right, over here, y minus 3 squared is always greater than or equal to 0, again, because they're both being squared. All right, which means, so therefore, that's one word. I think there's an end at the end. No, that doesn't look right. I don't spell very well. You already know that, though. Anyway, therefore, the function itself has to be greater than or equal to 4. I keep wanting to write 14. Has to be greater than or equal to 4, right? Because if this is 0 and this is 0, the function's equal to 4. If x or y is anything greater than -1 or, I'm sorry, 1 or 3, this is going to be positive. All right. So that makes the function always greater than or equal to 4 for all xy. Okay. All right, which means that f of 1, 3, which is going to be the extreme point on the function, is going to equal to 4, is going to be a minimum. All right, so if the entire function is always greater than or equal to 4 for all values of x and y, 4 is the lowest point on the function, and that makes it a minimum. And if I, let's see if I can do this, if I switch over to GeoGebra, you can see, all right, you can see there what this looks like. All right, so this is a paraboloid, as I mentioned before. And this is the point right here where x is 1, y is 3, and z is 4. Okay. All right. So let me switch back to my whiteboard. All right, so again, with a function like that, it's not too hard to see what's going on. All right, now that is a function that actually had a local minimum. So if we take a look at a function that may be a little bit different here. All right, let's scroll down and take a look at this function. All right, so if we take a look at the function f of xy equals y squared minus x squared. All right, again, if you go back to that section where we talked about the quadratic surfaces, that is a hyperbolic paraboloid, and we'll take a look at that in a minute. Okay, so let's take a look at the same process that we just did. All right, looking for local extreme points. So I'm going to take the first partials. All right, so with respect to x, that's 0. This is minus 2x. With respect to y, this is 0, and that is 2y. All right, so there are your first partials. So if I set these equal to 0, that gives me x equals 0. And if I set this one equal to 0, that gives me y equals 0, which gives me 0, 0 is a critical point. All right, so we need to take a look at what happens near 0, 0. So this is kind of similar to what we did with the limits, right? We want to see what the function is doing near 0, 0. So I'm going to look along some paths. If I look along the x-axis, right? If I look along the x-axis, that's where y is equal to 0. Then I have negative x squared, right? So then f is negative x squared, which is always less than 0. All right, and that's true for all x. Along the y-axis, that's where x is 0. Then f becomes y squared, which is greater than 0 for all x. This is true for all x and y. Oh, hang on, I can't do it that way. This one's true for all x. This one's true for all y. Okay. So every disk around 0, 0 is going to give me values where the function is both positive and negative. All right, so every disk around 0, 0, F is both positive and negative. All right, now that means that there's no extreme point, right? So no extreme point. And in fact, a point like this, all right, a point like this where you have, as you take the limit, as you approach your critical value and the function is both positive and negative everywhere in that disk near your critical point, this is called a saddle point. All right, not every function that gives you a critical point that's not a max or a min is a saddle point, but in this case, it is because of the way the function behaves here. And if we take a look at GeoGebra, okay, you'll see what we have here is, here's 0, 0. All right, I'm going to try and move this around a little bit. Here's 0, 0 right here. All right, and if I take any kind of disk around 0, 0 in any direction, all right, I've got an upward facing parabola here. And if I turn it this way, I have a downward facing parabola here, which is what gives us that saddle shape. All right, hence the name saddle point. All right, so that's how you describe a saddle point. Now, we want to take a look at a test that is a little more structured than what we've been doing. All right, so far we've taken a look at some basic algebraic methods for dealing with these. But what we're going to need is a more structured test. Let me just start a whole new page here. All right, and that structured test is what we're going to call the second derivative test. Okay, so I need a pen. Wait, where is my, there we go. All right, so the second derivative test, if you recall, we had a second derivative test in Calc 1. Hang on. VE, derivative test. All right, we had a second derivative test in Calc 1. And in Calc 1, you would take the first two derivatives, you would find the critical points with the first derivative, and then plug those critical points into the second derivative. And if the second derivative was positive at a critical value, that means the function was concave up at that critical value, making that critical value a minimum. And vice versa. If the second derivative was negative at that critical value, that means the function was concave down at that critical value, so you had a maximum point. That's, again, of course, it's a little trickier with functions in R3 because you've got that other dimension. So we're not just moving left, right. We're moving left, right, up, down, back, forth, like that. So we need a few conditions here. And the first condition is that the second partials of f are continuous near our critical value. All right, so let's do this. Suppose AB is a critical value. We need that first. All right, we need the second partials are continuous. O-U-S. Are continuous near AB. All right. And we need the first partials to be 0. Right, okay, well that's kind of implied up here, but I'll write it anyway. And fx AB is 0, fy AB is 0. These two basically say exactly the same thing here, okay, just so you know. Making AB a critical value. All right, then we define a function. All right, so then we're going to let this function that we call capital D is going to be, oh, actually it's D of AB, right, D of AB. All right, because we never calculate it without the AB. That would get a little messy. All right, so D of AB, let me make sure I get this right, is going to be the second partial of x with respect to x of AB times the second partial of y with respect to y of AB minus, all right, now we need to multiply the mixed partials, but remember, if the second derivatives are continuous, then the first partials have to be the same. All right, so I'm going to write this as fxy of AB squared. All right, so we define this function. This function is our discriminant function. All right, this is going to be what helps us determine what we've got. All right, so now we have conditions. If D is positive, so if D is greater than 0, and the partials with respect to x, right, fxx of AB also positive, then FAB is a minimum. All right, then okay, so our discriminant function is positive. The second partial of x with respect to x is also positive. Then our function has a minimum there. Okay, here we go. All right, so if our discriminant function is positive and fxx of AB is negative, all right, then FAB is a maximum. Okay. All right, now the saddle point. If D is less than 0, all right, so if our discriminant is negative, then FAB is a saddle point. All right, so if the discriminant is positive, right, if our discriminant function is positive, all right, then depending on the sign of the first partials with respect to x, we get either a minimum or a maximum. All right, if fxx is positive, we have a minimum. If xxx is negative, we have a maximum. All right, if D is less than 0, we have a saddle point regardless of everything else. And I'm leaving out one unfortunate consequence here, which is what happens if D is 0. All right, if D is 0, we have no conclusion. All right, then there's no conclusion. That doesn't mean that we don't have a maximum or a minimum or something else. It just means that the second derivative test can't be applied. All right, and in that case, we're going to have to look at other methods. So those other methods could be what I did in the previous two problems, or what I'm going to do in the next video. All right, but before we get to that, let's take a look at using the second derivative test in an actual problem here. All right, so I have a function, and my function, f of xy, is going to be x to the fourth plus y to the fourth minus 4xy plus 1. All right, so the first thing we need to do is find the critical points. So that means I need fx. All right, so with respect to x, that's going to be 4x to the third. That's going to be 0. With respect to x, that's going to be minus 4y. And with respect to x, with respect to anything, that's going to be 0. All right, fy. All right, with respect to y, that's going to be 0. That's going to be 4y to the third. That is going to be minus 4y. And that's going to be 0. All right, so we have two functions here. Now I need to set each one of these equal to 0 and solve them. Now here's the thing. These are not simple functions. All right, the easiest thing for me to do is going to be to solve one of them for, yeah, that's wrong. Sorry, that's an x. Oh. 4x. And if, believe it or not, I heard all of you yelling at me through the video about that, which is how I noticed it. So thank you. Anyway, I need to solve one of these for a variable and plug it into the other one. That's going to be the easiest thing to do here. So I'm just going to take this one and solve it for y. All right, so if I divide through by 4 and bring y over to the other side, I have y equals x to the third. All right, so I'm going to take y equals x to the third, and I'm going to drop that in. I'm going to take this, and I'm going to drop it in to this equation right here. All right, so that's going to give me 4, and then that's going to become, when I plug that in there, x to the 9th minus 4x equals 0. First thing I want to do is get rid of the 4. All right, let's see, I can take out an x. I can factor this into x to the fourth minus 1, x to the fourth plus 1. This one is not going to yield any zeros. It can be factored further, but I'm not going to bother because it's not going to yield any zeros. This one can. All right, so this is going to be x squared minus 1, x squared plus 1. Again, this is also not going to yield any zeros, but this will. And I guess technically I could stop here. I don't need to factor this further, right? I'm going to have x equals 0, x squared minus 1 equals 0. So I have x equals 0, and I'm going to have x equals plus or minus 1. So x equals minus 1, and x equals plus 1. All right, so I have 3x values. So I'm going to take those 3x values, and I'm going to go back over here to get my y values. All right, so if x is 0, right, if x is 0, y equals 0 to the third, which is 0. If x is negative 1, then y equals negative 1 to the third, which is negative 1. And if x equals 1, then y equals 1 to the third, which is 1. So I have three critical points, three critical values. Right? I've got 0, 0. I have -1, -1, and I have 1, 1. All right, so what I want to do now is use the second derivative test to determine which of those is a maximum, which is a minimum, which is what. Okay, so I have to go back to my test. So my test says I have to look at fxx, fyy, and fxy. All right, so let's calculate those over here really quick. So I'm going back up to here. So I guess I'll just do it that way. fxx, xy. All right, now again, with respect to x, that is going to be 12x squared. That's going to be 0. All right. fyy, that's this one. With respect to y, that's going to be 12y squared. That's going to be 0. And then I need fxy. Remember, I don't have to do fyx because my first partials are continuous, which means the second mixed partials are going to be the same. All right, so fx with respect to y, that's going to be 0. That's going to be -4. All right, so one important thing that I want to note here is, remember, part of the definition of the second derivative test had to do with what was happening with fxx. All right, and if we take a look at fxx here, 12x squared, doesn't matter what x is, that is always positive. All right, so we have the first part, or really the second part of this, which is that this is always positive. This is greater than or equal to 0 for all x. Okay, so as long as x is not 0, this is going to be positive. So let's deal with these two. Okay, let's deal with these two first. Let me just check something real quick. It is definitely yes. Okay, that's fine. All right, so let's deal with the two non-zero points first, then we'll deal with the 0 point. All right, so I'm going to come over here. Actually, I'm going to grab my pen first. All right, so we calculate d is going to be fx, let me just write it down real quick, fxx times fyy minus fxy squared. All right, so for 1, 1, all right, so d of 1, 1, fxx at 1, 1, all right, so at 1, 1 is going to be 12. fyy at 1, 1, again, put in 1, it's going to be 12. Minus fxy is always -4. Now, do I care what this number is? No, I don't. What I care is that it's positive. All right, so my discriminant function is positive. My first derivative is positive. All right, that makes this, I'm just going to make a note here, that this is a minimum. All right, let's check d of -1, -1. All right, well, fxx -1, that's still going to be a positive 1, so that's still going to be 12. fyy of -1, -1, again, -1 in there, that's still going to be a positive 1, so that's still going to be 12. minus this is constant, so it doesn't matter what f is. That is still going to be negative 4, which means that is still going to be a minimum. All right, so those two are clear. All right, D00. 0. All right, let's take a look at D00. The only way that this can be a problem now, well, let's just do it. All right, so 0, 0. All right, if I put 0 in here, I'm going to get 0. All right, that's good. 0, 0. If I put 0 in here, I'm going to get 0. Okay, that's fine. Minus, this is a constant function, so it doesn't matter what I put in. It's going to be negative 4, which means this is less than 0. Whoop, I forgot to put the 0 in there. Less than 0. All right, so remember, the saddle point, it doesn't matter what fxx is, because in this, it doesn't matter what, fxx is, because it's, if the d is less than 0, there's no second condition. So this is a saddle point. Okay, all right, so we have a function that has two minimums, and between those two minimums, there's a saddle point. All right, and every semester I get asked what this function looks like. I'm going to show you, but I always describe it the same way, and that is the bottom half of Patrick's star from the waist down. Okay, so we are going to take a look at the, let's see, did that switch it? Yes, it did. Okay, so here are your two minimum points. They actually occur below. Here are your two minimum points. Here is the saddle point. All right, so again, it's kind of elongated, but yeah, the bottom half of Patrick's star from the waist down. Okay. All right. So the second derivative test will work, again, as long as you don't have your discriminant being 0. You can find max points, min points, saddle points predicated on the second derivative being easy to deal with. All right, so for the function that we just looked at, right, it wasn't difficult to take the second derivative. It wasn't difficult to work with the second derivative. The problem that we're going to run into, all right, is sometimes the second derivative is a nightmare. All right, and we're going to want to have another method. Now, the other method that we're going to talk about, and I'm going to talk about this in the next video, is what's called Lagrange multiples, Lagrange multipliers. All right, and they tend to be used on problems where you have more of an application and a constraint that is a little more complicated. All right, so I'm trying to decide if I want to start this now or if I want to start this. No, I'm going to start this in the next video. So I'm going to end this video here, and we will talk about the Lagrange multipliers and the application problems in the next video.